All right, here we go. So today we're going to look at work, energy, and the work energy theorem. We're going to put it all together. Also look at efficiency. All right, so here's yesterday's lab. I kind of see where this is. Here's the pole, ramp. We got a force sensor and our car or a block. So if you see this and it's a problem and you want to solve something about it, what's typically going to be the first thing you're going to do? Free body diagram. I think that would be a very safe bet. Go ahead and draw a free body diagram. So here's our gravitational force, straight down. Here's our perpendicular. You guys are familiar with that. Parallel, nothing new. What's this? Normal. Normal, which is equal to perpendicular, as long as string is parallel. There's no other forces acting on it at any weird angles. And I asked you guys to make sure you did that. And this is tension. Tension, which is also the effort force. Effort. Okay? And effort force is what you are doing to the machine. The amount of force you're exerting on the machine. Then the machine is going to exert a certain amount of force for you. So we'll get to that in a second. Okay, so we're gonna give this a new name, effort force, and we're gonna apply that here in a minute to find efficiency. Work in and work out. All right, what else do we have? Incomplete. Friction. Was there friction yesterday? Yes, because I heard Brandon pulling his car up and he was going. Was that yours? It was kind of squeaking? Yeah. So you can hear that friction. What else? Or maybe that was just Brandon. Okay. What else we got? One more thing, come on. I've actually already drawn it. That's your hint. I've actually already drawn it. That's parallel. Very good. Very good. On a test, if you didn't put it there, I wouldn't count on it. If you did put it here, but I think it's good to show it right here so you can clearly see everything that's going on. So I think that's a good free body diagram. That covers everything. Have I missed anything, John? I don't think so. I think that's got it. All right, so I'm going to minimize it. And I'm going to introduce a new term. Work in. What's the definition for work in? Tesh. Force you exert on it based on the force that you exert on it. So it's work in is the force you exert times the distance that the object traveled as a result. Effort force times effort distance is what we call that. So let's go back over to our picture and identify our effort force. Effort force. Here, I'll do that in blue. Where's my, effort distance? Amy? Good. So it's how far it traveled. That's going to be our DE. Okay. How far the block traveled along the ramp. That's our DE. Very good. So let's look at the equation for work in. What is our effort force? Just Fe. Just this Fe, which happens to be the tension. So work in is tension times the displacement, how far it traveled. In this case, it's just the tension. We can say displacement. We can treat it as yeah, we can treat it like that. Started from 0 and it ended at whatever 1.1 meters, 1.1 minus 0. Okay, let's look at workout. What is workout? What did you read about workout? Sean, what's workout? Obviously it's force times distance, but what force?
When you feed the force of
Neither one of those quite make sense. There are words involved that you should put together. Somebody help us out? Michelle's tired today. Huh? Force of friction. By the way, you can find work done by force of friction, but that would not be the workout. Force of friction also does work in. I'll talk about that in a minute. Michelle. Tesh thought I was going to say Tesh. That way. Michelle. Repeat the question, please. The question was, what's the workout? What force is done in workout? In other words, what is the machine doing? Work in is what we do to the machine. What is the machine doing for us? Franz? Force output, we're going to call it R for resistance. And the distance, output, or we'll call it R for resistance again. So in this case, it's R. And where's that on our free body diagram?
where you subtract
Where is it down here? You said friction? No.
the subtract.
Force of gravity is our resistance force. That's exactly right. This is why we are using a machine. Because we can't lift it or don't want to lift it or it might be dangerous. So here's what I mean. We've got this big old heavy thing right here. And I got to get it up here and into the back of a U-Haul truck. And this is a U-Haul truck. So I can do a couple things. I can lift it up here. Xavier's already on the truck. He can then take it to the back. Or if I'm by myself, some of you might try this. That's kind of dangerous, right? And plus, you can't do that for all 700 boxes that you get. One after the other, lifting your entire weight of your body plus the box. So it's not very smart. So what we want to do is stroll up nice and smooth up the ramp. Take your time. What's the trade-off? I have to travel for the distance. How many of you can lift a car with one hand? Everybody in here can lift a car with one hand. You just require a machine to do it. It needs to be a well-lubricated, what do you call it, Jack? Jack. If it's got a lot of friction, you may have to two hands. But if it's really, really greased up, and because if you ever get that grease on the pants, Jack, it makes a big mess. But you can with one hand. It's a good one. Some of them you crank, some of them you turn. You turn. About 30 turns into it, you'll notice the car moved an inch. 30 turns into it, moved another inch. So you got to turn it like forever, but the car will eventually go up high enough so you can take the tire off. And so anybody can do that. It doesn't matter how big you are. The hardest part is getting the lug nuts off, not lifting the car. If you've ever changed the tire. Anybody change the tire? Good. Y'all all need to have experience doing that. So girls, you need to go home and say, Dad, show me how to change the tire. Mr. Wells said, I need to learn how to change the tire. Well, you need to learn how to use your body weight to get lug nuts off. Because if you're stranded out, you want to be able to do it, huh? Yeah. Unless you have, yeah, that's better. Because then you can take leverage from two sides. But if you just have the one, then you've probably got to kick it, which could break the stem of the, but probably it wouldn't. And that's what I have to do. They're so tight, I can get it off without getting hurt. But anyway, so here we go. Resistance force is the gravitation force. The payoff here for our workout is that we have to travel a long distance. versus the machine, which just goes what this height. This is why we have the machine also. Because we're trying to overcome the weight of the object, and we're trying to overcome this distance that we have to carry the weight of that object. So what we do is we exert a smaller force, and what is the effort force equal to in this particular example? What is the tension equal to? Friction and parallel. And we hope that the friction and the parallel, especially if it's on wheels, the friction and parallel should be less than the gravitational force. If it's not, then it's not really doing us much good. But parallel, we know, is much less than the gravitational force, especially if that angle is small. And you guys found out that as that angle got bigger and bigger and bigger, that force got bigger as the angle got bigger. So the distance got smaller as the force got bigger. But the friction would also, well, no. Yes, correct. So the normal force changes. Good, very good, McKay. Very good. You're absolutely right. Until finally it's just being hung in the air. Okay, so workout is resistance force, which ends up just being gravitational force. In this case, it's not all problems, just this problem, times the height. In just this problem. I don't want you to think that's the definition for all workout. But in this problem, it's gravitational force times the height of the ramp. This is tension times the length of the ramp, d. No. This equation is always true. This is just specific to this particular problem. And same thing here, this is always true. But Fg times h is specific to this problem. Okay, so we've broken it down and we've identified where the Fr is, the Fe, the Der, the dE. Oh. Let's go ahead and do that now. Somebody brought up, it was Amy brought up friction. So yesterday, when you were getting the slope, by the way, just a quick recap. Yesterday you did force and time. You took the mean, which was the average force. Okay? If you did this, that means you were accelerating. That meant you were decelerating. So you tried to stay nice and even, right? Or at least pick the ones that were even. Okay, that's just a recap from yesterday. Then you graphed data. You got an inverse curve. And we found there's two ways to straighten this. Alex, do you remember? Two ways to straighten this. Good. Take the inverse of x, and you guys got boom. And the other way, which is not what we wanted to use in this particular situation, and if you didn't know that, or maybe you're a mathematician or a physicist and you're trying to find a relationship, you're not sure, you can straighten it, but the variables don't really make any sense, then you know you're probably at a dead end. The other way is take the inverse of both the y and the x, and that would give you, if any of you did it, it would give you a straight line like that. We're going to do that next semester. That'll become important for next semester. But this one, we did this. We know y equals mx plus b. So we got f equals something, 1 over d. Multiply d on both sides, you get fd. And you're like, oh, that's work. So you knew right away that the slope was work. But before that, you may not have recognized that work was slope. Okay, recap from yesterday. Now, our question is, what work did we find? Because I've just shown you there's different works, isn't there? There's work in, there's work out. Then we just acknowledged that there is work done that could be positive and there's work done that can be negative. So which work did we find yesterday? Josh. We found work in, and be specific as to which force we used. the tension force, which was going up the ramp, the same distance that the object was moving, so it was positive. Which was the effort force, which is different from friction. Can friction do work? Is friction a thing? Is it a person? Does it need to be a person? No, because work is force times distance. So, was there friction yesterday? Did the box move? What is the angle of the force related to the distance? No. So, here's the friction, and here's the distance. I'll put an arrow. That's not a 3 by that. So the angle is 180. Cosine 180 is -1, so this is negative work. So friction can do work, but we did not identify friction yesterday as our force. We identified the tension, which happened to be equal to, yesterday our tension, was equal to parallel plus friction. How do we know it was equal to parallel plus friction? This is very important for tomorrow's test or Friday's test, like a concept. Peter, how do we know that the tension was equal to the parallel plus the friction? How do we know that this is equal to those two in yesterday's lab? There's something I told y'all to make sure you're doing when you were pulling yesterday. Huh? Keep it parallel, but something else. Brandon? You're going to say parallel? Josh? Constant velocity. Constant velocity. So we don't want to accelerate it. And we made sure it was constant by looking at our graph and seeing that the graph kind of tried to stay relatively straight. It had a trend that was steady. Okay? So, I'm sorry, not U. Acceleration equals 0 in yesterday's lab. That's why they were all equal. Because acceleration was 0. Huh? Tried to. I mean, it wasn't perfect, but the graph would help tell you. Or if you started to accelerate, you select those data points that would give you that mean that was showing a 0 velocity. 0 acceleration. Alright. So, back to friction can be negative, but yesterday we used the effort force, which is positive. Now, let's do a couple terms here. How do you find efficiency? Now, here's what I mean by efficiency first. We know that the conservation of energy applies here. So the work, by the way, what's the unit for work? Joules. What's the unit for energy? Joules. So conservation of energy is applying to work. So the work in should always equal the work out. Theoretically. Does it? Never. Have scientists tried to make a machine that had work out equal work in? It's called a perpetual motion machine. A machine that will last forever once you get it started. It's conserved. So that means it has minimal interference from outside forces and from friction. But you know that whenever you're in motion, even the molecules are moving, and that's going to cause energy to dissipate. So you have to be at absolute 0 for this concept to even work, which doesn't make sense because the whole purpose is to move. So efficiency is the concept of, or it's the ratio between the work in and work out. So it's work in, it's work out over work in. And how do you remember that? Because it's not on the equation sheet. Efficiency is not on the equation sheet, so you got to memorize it. So how do you memorize this? Well, you got to remember the concept. Efficiency is always going to give you a number less than 1 because you're always going to get less out of the machine than you get into the machine, than you put into it. Always, because energy is lost due to friction. If work in is always bigger than work out, that gives you a decimal. If you get them backwards, you'll have a number greater than 1, and you'll know you made a mistake. Because you cannot have an efficiency over 100%. And so it's going to be a decimal times 100. actually put a percent there, and they give you percentage. Efficiency is work out over work in times 100. This tells you how much energy was lost due to friction. You might want to write that down. It tells you how much energy was lost in the system. So if you have a machine that is only 60% efficient, that doesn't necessarily mean it's a bad machine. It just means that there's a lot of parts to it, and all those parts have contact with each other, and so there's energy being lost. But you can have a machine that has 60% efficiency, yet the amount of effort that you have to put in is really small. Like a pulley system that has 4 or 5 pulleys in it. A complex pulley system, you can pull a very, very, very large, you can lift a car. Again, with one hand, but I mean the whole car at one time. With a pulley, if it was efficient. You would just have to use this much string. Pulling it, pulling it. It starts to lift, it's lifting! And just all the string is, big rope at your feet of all this string. But definitely possible. In fact, you can lift your body up on a pulley system, up a tree. And if you've ever had a chance to do that, you just got to pull, but it's easy. Alright? If it's closer to 100% efficiency, that means probably the amount of effort you have to exert equals the amount of weight, which isn't really helping you that much. But if you can't hold on to a tree, then maybe it's better just to pull yourself up. That's the single point. Anyway, here's efficiency. Now here's another equation for efficiency. You guys know it? Josh? There you go. So, and to remember this one, by the way, these are going to be equal to each other. These are equivalent. Either one's fine. You could learn either one of them. This stands for mechanical advantage, and this one's ideal mechanical advantage. Just remember 2 initials over 3 initials. So let's define mechanical advantage. Okay. The ratio of forces showing it shows energy loss. This system shows energy loss. Ideal mechanical advantage is a ratio of distances. It shows, I shouldn't say shows, and is a perfect, okay, now, and represents a perfect system. So whenever we say that in physics, we mean theoretical. That's the concept. Nothing today is counterintuitive. Everything today is pretty straightforward, just a couple definitions, no big deal. Okay. So mechanical advantage shows energy loss. Well, what is the equation for mechanical advantage? Let me show you. Mechanical advantage is perfect. Ideal mechanical advantage is Dieter. So just remember Ferfadieter. Ferfadieter, say it. Michelle, say it. Say it by yourself. Ferfadieter. You have to. Very good. It's the funnest word to say. Ferfadieter is awesome. I say we make a rap song out of Ferfadieter.
Yeah, quick verse.
He'll just add the bass to the story.
Every song from work out.
I don't want to press your ear.
Ferfadieter. Easy. Ferfa is a ratio of forces that shows you mechanical advantage. Dieter is a ratio of distances. It shows you ideal mechanical advantage. Now, here's a deep conceptual question. Although it's not counterintuitive, it's fairly straightforward, but there's some depth to it. Why is it that this ratio is what's actually occurring in the machine and shows energy loss, whereas Dieter does not? Why don't y'all discuss it? 2 minutes. I wish I had autoresponders to this. Discuss it. Discuss it. I'm going to pause. All right. What'd you come up with, Grace? What does Grace think? Jillian, what do you think? I like that. I have close to no idea. I might could offer some suggestion, but it's close to no idea. I've never heard that before, Jillian. I like that. I'm going to use that next time to explain this part about organic chemistry. Yes.
What I was thinking, hypothesizing from this, is that mechanical advantage is showing the energy loss and how it's changing
Why?
friction.
How?
Friction.
Why? How? How does this show friction? This does not.
Well, it's just and it's showing the distance change if it were a perpetual motion machine that is speaking.
So now
I
you
guess
start to
it's
veer off. You were really good, and all of a sudden I asked how, why. But you're on the right track. Continue, Grace, or add something different. No, this is not work. This is force. There's no work here. There's no work here. Now, the ratio of these to each other is work. Okay? But right now we're just looking at a ratio of forces. Okay. Go ahead, Josh.
The distance is determined by the machine you build. The way you build the machine is fixed.
Now,
Your
Tish?
force is up.
Okay, finish.
The force is acting on other forces that don't apply to the distance. It's just like force you have to apply.
Okay, getting better. Tish?
You're using friction to calculate mechanical advantages. That's considering all the resistance and friction.
Okay, so that's what Josh said. Good. So, in terms of the forces, that is only taking, that's not necessarily taking all forces into account. So in a free body diagram, we don't always account for every force, like air resistance, and maybe there's some friction we haven't taken into account. So there's also thermal kinetic energy. There's all kind of forces going on. There's electromagnetic, there's electrical forces, there's magnetic forces, there's even light hitting the molecules causing thermal kinetic energy to go. I mean, it's just ridiculous amount of forces happening here. So this is not complete, is what that means. This is incomplete. This is complete, though. And by the way, let's go back to forces. This is involving contact between two surfaces. Is there any contact when it comes to just something moving in terms of measuring its distance? It's in contact, but the distance it travels has nothing to do with contact. That's just how far it traveled. So this is perfect. There's nothing else involved. It went this far, and it went this far. The ratio between those is ideal, but this never matches this, because this is not taken into account everything. This is. Does that make sense? So distance is not, nothing's interfering with distance. Air resistance doesn't affect its distance.
Oh, I get you.
Does that make sense?
Yes, totally.
Air resistance might slow it down, but it's still going to travel to here. The ramp might heat up, but it's still going to travel to here. So this is complete. But this is not taking into account the fact that there's energy being lost, which is what you originally said, and then we say because of the contact, because of air resistance, whatever. So there's other forces here. If we could write them all down, then maybe it would be closer to being complete. Okay? So we put these into that equation, and we get the same answer. And that is perpendicular perf over d air times 100.
That's
That is efficiency. Or just say MA over IMA. And of course, you notice you got a fraction in a denominator. So you can flip that. So that becomes FR times DR over FE times DE. FR times DR, let's look at that. Let's take this and work it out. If you work this out, it's FR DR over FE DE, which we've already said is work out over work in, which we already said was the other equation. So is it mechanical advantage and work out over work in really the same? Mechanical advantage over MA over IMA is the same thing as work out over work in. It's the same thing. They're the same thing. Further over feta.
Yeah,
Further.
if those two are which ones that within those two further
Ideally. Yes, ideally. Okay, questions on mechanical advantage, ideal mechanical advantage, efficiency, any of these things. And of course, you'll practice here in a minute. We're almost done. I'm going to show you one more thing, then we'll start practicing. Does DR equal DE? No.
okay, so let's say that's my so let's say the length of the string is like, I don't know, 4 or 5 inches. So DE would be 4 or 5 inches.
The tension string here?
Yeah.
The length of the string has nothing to do with it. It's how far the box moves.
So then how are they not
The DRDE? Because DR is how high it is, in this case. And how high you raise it and how far you have to travel to get there are two different things. So a U-Haul truck could be 3 feet off the ground, but the ramp could be 7 feet long.
so you have to be 7 feet, which was
So you travel 7 feet,
so that
and the machine says, I'll tell you what, you travel 7 feet, and I'll make sure he gets 3 for you. And then the machine says, I'll tell you what, I'll lift the whole weight for you, if you just lift the parallel component. They'll see you through. And you're like, no. So ramps, wheelchair. You don't see people in wheelchairs jumping up on a U-Haul or going up steps, although they people that can do it, they're strong. You know, hop up and see those stuff guys. But typically they're using the wheelchair ramp. And how's a wheelchair ramp? It's a gradual slope. That means they have a long distance to cover, but it's very gradual and safe. And also winds. Why doesn't it just go up one nice steady incline? What if they get tired or slip? They're like, oh. But if it's winding, the worst thing it can have is whoa. Then stop. Then you go back.
You might go farther, so your life becomes less.
And so most people that are not disabled and healthy are not going to take the time to walk through the wheelchair ramp that's winding like that. You're like walking back and forth. And the person you're walking with is already upstairs and they're gone. But if it's a small, gradual, some people will opt to take that just to avoid a step.
really,
I have to admit I've done that. If it's just a short, there's not a winding wheelchair ramp. It's just a short little, I guess maybe it feels better to walk up that crack and take a step. Because when you take a step, you're lifting your entire body up. It all comes out to be the same, right? All right. Now, the belted strength, so I'm going to introduce one more thing, and then you're on your own. Here we go. This is on web science stuff and test reform. Here we go. It's called the work energy theorem. So, all right, we're going to look at work energy theorem. I'm going to introduce that. Work energy theorem says that work equals delta kinetic energy. That's it. Work equals delta K on the equation sheet. Now, off to the side, let's talk about KE and PE for a second. What is PE? That is potential energy. And PE equals PE equals the actual equation. mgh. And by the way, that is only gravitational potential energy, which is energy based on its position from the ground. So this has greater potential energy than this because of its position. And you're like, really? And you say, well, yeah, it really does. And I'll give you an example. So here's a marble apple. It's a marble apple. So, you know, it doesn't have much energy, you know. Doesn't hurt my hand. But if it drops and falls off and hits my foot, it breaks my toe. That's a lot of energy. Constant. We can't do it. But if it's right here, and then it falls over and hits my toe, that's not going to hurt. Okay, you're like, duh. Because there's nothing in this section that's counterintuitive. Very straightforward. And you even learned some of this in middle school. All right, whereas KE equals kinetic energy. And that, by the way, potential energy, this is just gravitational. There's also elastic potential energy, 1/2 Ka squared. There's potential energy in the nucleus of an atom. There's different types of potential energy. Kinetic energy is usually pretty much the same everywhere. 1/2 the mass times the velocity squared of that object. Okay? It's measured in joules. Okay, so going back to the work energy theorem, what is work? Yep, net force times distance. What is change in kinetic energy?
mv naught squared mv f squared.
F? Oh, yeah, final. I just use it as plain. Minus 1/2 mv naught squared. You guys use F and I, maybe? Final and initial. This means final kinetic, initial kinetic. So here's the whole equation worked out. And what is net force? The sum of all forces that act on an object, or to put it in motion, or keep it from being in motion. So whatever all those forces are, you would write them there. The distance that it travels as a result of those forces goes here, and then the kinetic energy. So very interesting. You can begin to calculate things based on a different set of equations. You can calculate kinematics using the work energy theorem. Let me go ahead, Josh. Yes. And then you can actually just say, well, if F equals ma, then we're saying mad equals work. So work is mad. Or work it equals delta KE. So you can, if you incorporate acceleration, you can do that. Or maybe acceleration becomes v minus v naught over t. Plug that in. Factor out m's. You can do all kinds of stuff. But let's do this one. I like this. There's work energy theorem. Let me do this. Here's the last one. Let's do potential and kinetic. Potential and kinetic. Alright. If you're, let's say you're on a ramp. You're at the top. This is bottom. And it's traveling down. Where's all the PE? PE. So this is max, you're saying? Where's the minimum PE?
Bottom.
Well, I mean, if it's not,
Assuming it stops there. Where is KE in this process? Where's KE max? And KE min?
Bottom's minimum, that's top.
So it's opposite, right? And then in the middle should be about 50% PE, 50% KE. 80% down the ramp, it should be about 80% KE, 20% PE. They always add up to be 100% minus energy lost in the system. Okay, we're assuming theoretical here. So, check this out. You're going to love this. You're going to love this. All right. So, would you agree with this statement? Maximum amount of potential energy here should equal the maximum amount of kinetic energy when it gets to the bottom, assuming no energy is lost. Okay? Theoretical. And this is mgh. What h? Max h. It's the highest point. Equal 1/2 m. Which v? Final v. Let's solve for v. Divide by 1/2 m. Divide by 1/2 m. What happens? V equals the square root of 2gh. Well, no, this is going to trip you out. Watch this. Now, how did I get that? Those that are writing this down, all I did was set them equal to each other and solve for v. Now, watch this. Do you remember this equation? Vy squared equals v naught y squared plus 2ad. Or 2ay, actually, is what we called it. That's what we called it. 2gy. We just found that, didn't we? Take the square root of both sides. If the initial velocity is 0, vy equals square root of 2gy. 2g height is vertical distance. Same thing. They're the same thing. So energy, work energy theorem, energy, kinematics, they're all the same thing. You can use any of them to solve an equation depending on the variables that are given in the problem. So on tomorrow's exam, feel free, if you want, to solve a slightly different way if you're comfortable, solving using energy. Maybe an old problem that I gave you from the beginning of the year, like kinematics, feel free to solve it this way. So here's a problem. Can you solve for the velocity of an object that's dropped from the top of a tree, and all you know is the height of the tree?
Yes.
If PE equals KE, the energy of the cat in the tree before it falls equals the velocity at the bottom, equals the kinetic energy. So mgh, remember, if you're solving for the v, notice the m's cancel, so you don't even need to know the mass of the object. You know gravity. If you're given the height, you can solve for the velocity. Could you have done it with kinematics? You assume v naught y is 0, and gravity is negative 9.8, and you are given the y, so it's really the same. They're just slightly different approach. Yep.
You said work was equal to the change in kinetic energy,
Yes.
but what if there's
Now,